Hello everybody, I will start my today another live coding session. So today I solve this question. Binary tree path. Given the root of a binary tree, return all root to leaf paths in any order. A leaf is a node with no children. Okay, quite a simple question. Let me clarify my understanding first. So in this question, I'm giving a root of the binary tree. So this should be tree node class. And I will return this like this, list of strings. Each string represents a tree path from root node to the leaf node. Okay. And the path in the list can be in any order. Okay. So that being said, let me take a look at some examples. But one thing I'd like to confirm is if this root can be null or not. And I can see that here, the number of nodes in the tree is in the range 1 to 100. So I can say root isn't a none. So I can create at least one path, even if the tree has only one node. So let me write it as the edge case. So if I'm given only node 1, then I should return this string. Okay, so let me take a look at some other examples like this. Yep. So in this case, the path I have is 1, 2, 3, 1, 4, 5, and 1, 4, 6. So I should return so first 3. Okay. When I take a look at the examples, I can find that node values are concatenated with the arrows. So first 3, it should include this. And also this should include 1, 4, 5, and 1, 4, 6. Yeah. So I've seen some examples. So let me think of the algorithm. So because I need all the I need the whole path string from root node to the leaf, each leaf. I have to keep track of it when I go down the tree. So I can use the backtracking. So what I mean to say is I keep track of the node sulfur, or I can say bulk sulfur as the list. And this can be, okay, and basically do the recursion from root node. So let's say I start from node 1 and then I go to node 2. Here I append 2 to the bulk sulfur. Then I go to node 3 and I find that this is the leaf node. So I can think of this as the base case. I don't traverse anymore. And I build the string from bulk sulfur. Yeah, I join strings. And I create it and I append it to the returned list. So after that, I come back to root node 3. I come back to node 2. And before going back, I pop out this 3 from the bulk sulfur list. So then I go back to node 2. The parent call of the recursive function. Then, because I don't have any child aside from node 3, I go back. So roll back node 2 from the bulk sulfur list and go back to node 1. And then I append node 4 to the Bard solver, and I keep going because this is not the child node, sorry, leaf node yet. So that's how it works. Okay. Base case is root is child node. Okay, that being said, let me get started with implementation. For complexity analysis, I will do it later. I think it's a bit complicated, if my memory is correct, for this kind of bug tracking, complexity analysis. Okay, so this is something to be returned in the end. I have the list of bars. Then I traverse from root node. Okay. And here, root cannot be known. Okay. That being said, if this is the leaf node, it's the base case. So in this case, this is the child, sorry, this is the leaf node. So I create the, wait. Because I've visited this node, I firstly add the bar to the bars list. As the string. Okay. Then here, I create the path. In this way. And append it to the returned list. Okay. And I return. But before returning, I have to roll back this change. So I do something here, and here I roll it back. Okay. So here in line 59, because this is not a leaf node, I keep going. If this is not num, so yep, I keep going. Or if right child is not num, I keep going with that. Yep. And in the child tree, the same thing happens, and in the end, the path is added to the path, path list. Okay, so this is it. Let me quickly dry run my code. So in the case when, this case, if there is only one node in the tree, let's see, there are those paths, the Bard software, they are initiated, and I traverse with root node 1. So here, root node is node 1. And serve.var software append root.var. So this is added. Okay. And in line 57, root.left is known, yes, and root.right is known, yes. So this is a base case. So here, path is created as 1, and this is appended to the server.path. So this is added. Okay. Then I go to line 66, and I pop out this one from bar software list, and I come back to the main function. And I return server.path, which is the list of string 1. Okay, this is as expected. So the observation I can make from here is the backtracking is working correctly, I think, because the added bar into the list is popped out in the end in line 66. The only thing I have to take care is I have to cover is line 61 to 65. So I cover only line 63 and 64 with this case. Okay. So in this case, let's start with root node 1. Here in traverse method, one is called. And this is not the, sorry, I append 1 to var software. And here in line 60, because root.left is not known, I go to line 64. And in line 64, this is true. So self.traverse root.left, which is node 2. So here I take a look at node 2. And yes, this is the base case. Oh, by the way, I append this 2 to here. And then in line 63, I can say this is a base case. So I create the string. Oh, the created string, the delimiter should be this one. So the right arrow. So I updated it. So now 1, 2 is created. So this string is added to server.path. Then I go to line 72, and this 2 is popped out. And I come back to the function called traverse1. And I was at line 67, no, 68. I go to line 69, but root.right is none, so I don't go into this. And I go to line 72, and I pop out this one. Then I come back to the root main function, and I return this string, 1 arrow 2. Okay. So I also pass this test case. This returned 1 arrow 2. Okay. So even though I haven't covered line 69, no, line 70, obviously this is correct. So I'm pretty confident my code. Let me submit. Good. Okay, accepted. Great. So let me quickly do the complexity analysis. So basically, if I have the node, this recursive function is called following the structure of the tree. So as I can see here, let's say the tree structure is like this. In this case, traverse method is called in this way. 2 and 4, and 3 is called here. Yeah. So now I will think how much time it takes in each method. So aside from the root reef node, this takes only the constant time, because I just had to take a look at the left child and right child and call the child function. Same for this. But for the ref node, the thing changes because I have to create the string path. So how much does it take? It takes the height of the tree because their exact tree is the height, number of nodes in the Bard software list. And for this and this. So let's say this is equal to O of n, or I should say, if the tree looks like the linked list, h is equal to n. So this is the worst case. So I will use O of n, and I find the upper bound of the time complexity. And now my problem is how many nodes there are in the given, how many leaf nodes there are in the given tree. So let's assume there are n nodes in the tree. So in this case, in the worst case, there are n divided by 2 leaf nodes at most. This is the case when the tree looks like a balanced tree. So now I found it. And for others, there are n divided by 2 first method calls, which takes only the constant time. So I can think of it in this way. O of 1 times n plus O of n times n divided by 2. So the time complexity should be O of n squared. Yeah. Okay. So this is the time complexity. For the space complexity, the data structure I need is self.path, but I don't include it because this is the returned list. And self.var sulfur, it can be up to O of h, so I assume this is O of n. Also, I have recursion stack. Same, this takes O of h, which is equal to O of n. So in total, it takes the linear space complexity. Okay. So I'm done with the complexity analysis. Good. Now let me quickly wrap up on today's coding practice. So today I answered the question, binary tree path sum. No, binary tree paths. And in this question, I was given a root of the binary tree, and I returned the list of all the path string from root to leaf. Oh, I'm saying the same thing twice. But sorry, so I'm given the root of the binary tree, and I return the list of string paths, which represent every possible root to leaf path. So I use the backtracking in this question. And every time I visit the leaf node, I create the path string and I append it to the returned list. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.